right. So, before we get going, make sure this is on the right thing. Okay, perfect. A couple of things I want to mention before we kind of dive into material here today. So, what's due at the end of the day? Friday. Yeah, so that second quiz and that second problem set. Okay, so we should have covered all the material that you needed to do both of those. We'll kind of revisit some of it today, just to kind of where we pick up where we left off. We'll then dive a little bit deeper into kind of simple linear regression. So the files I uploaded for this week are going to be where we left off. So I've kind of updated the PowerPoints. I always put up like more. I'm probably a little bit optimistic in how much we'll get through. And so sometimes there's stuff we don't get through. I'll go back and update the slides just to have what we covered that week. So I updated kind of those where is it at? Week 4 slides, just to kind of be reflective of what we covered. So we'll kind of start where we left off in week 5, and then we'll start multiple linear regression this week. I doubt we'll get there quite today. We might introduce the idea. We'll kind of dive deeper into it on Thursday's class. So that problem set and that quiz is due Friday. I have posted, where is it at? Here we go. That midterm practice already. We are still quite a ways off, so it's not till March 5th. I want to get up there as early as possible, just so you can kind of start to look at some of the questions that you'll be expected to answer. We haven't covered all the material yet, so some of it's going to look kind of foreign. I will get up later this afternoon, the third set of practice problems. So even though that quiz isn't due until the end of the day on Friday, if you want to start thinking about the next quiz, I'll get those practice problems up there. And then I'll probably post the third problem set sometime on Friday. And once again, the due dates will be a little bit further off, especially since the rate at which we're covering things now, it's probably going to be a little bit slower. And so it'll probably be the due date is like 2 weeks from when I kind of post that, which will be getting closer to that exam date of March 5th for that first midterm. Okay. So kind of just foreshadowing where we're going. Another thing I wanted to mention, if you haven't contacted me already, if you do have an accommodation through the AES department, if you haven't let me know already prior to that midterm, you need to let me know well in advance so we can kind of have something up. Other than that, I also updated the regression file that we were using last week to only kind of cover what we went through. And then I uploaded one for this week, which is kind of part 2. So that's kind of the one that we'll be using today. So I've already got that pulled open on the Stata. We'll jump into that at various points throughout the class. Once again, I don't think we'll quite get there today, but if we do, multiple linear regression is the next topic we'll cover. So for sure, we'll be using this do file on Thursday. Maybe just open it up and look at like the first example today if we get through things kind of quickly. Okay. And then any data sets that we would need for this week, I kind of have in that Stata file as kind of heading for week 5. Okay. So before we kind of jump into things, any questions for me logistically about the class or just anything before we get going? Okay. So I'll go through the first few slides very quickly because it's really going to be a review of what we talked about last week, just kind of reminding ourselves where we're at. So kind of what we're doing when we run these simple linear regressions is we're trying to come up with this predicted value that tells us the relationship between an X and Y variable, or that beta 0, or we kind of call that slope coefficient. Right? So the value that we are seeing from Stata is the expected value, right? Or is it's going to be from our sample data set, what did we estimate that relationship to be? There will be some true value if we had the population data, but we often don't have the population data. So if we were to take enough samples, we kind of said those sample coefficients, just like the sample mean, will be normally distributed around whatever the true population statistic is, right? So we usually only have one sample, but we know if we had 1,000, they'll all be centered around whatever that true value should be. We then kind of talked about that standard error of that slope coefficient is very similar to like the standard deviation of our sample means, right? So we can kind of think about, we have this estimate for the statistic. We have the variation that exists in our sample data from that statistic. We can then think about that sampling distribution. We could then think about doing hypothesis testing. We said for us, whether it's the intercept or the slope coefficient, we always start assuming that it's equal to 0. So we always have a two-tailed test. Okay. So almost makes it easier. We're always using this assumed value of 0. Our steps, look exactly the same as what we're doing for the sample mean, right? We use that sample statistic, that sample coefficient, we turn it into a test statistic. We then compare that test statistic to our critical values, or we use that test statistic to find the, so I can use the critical value approach, or I can calculate, or I can determine what the p-value is and compare it to alpha, right? So the steps really look no different from what we were doing before. We talked a little bit last class about standardizing variables, so we'll revisit this in Stata, just getting some more practice interpreting some of this output we see from this data. But just to kind of revisit this to see if we remember, if I scale a variable, right, what is that going to do to the statistical significance of my slope coefficient? So remember, these slope coefficients are always the effect of a 1 unit change in x on the predicted value of y. So when I scale them, the units of my x variable would change. So my interpretation of the slope coefficient would adjust accordingly. So let's say I had dollars instead of a $1 increase. If it now represents thousands of dollars, the change in my x variable would be an increase of $1,000. But when I take that coefficient and I divide it by the standard error, they're both going to have the same units. So regardless of what my units are, if I divide dollars by dollars or thousands of dollars by thousands of dollars, that's always going to cancel. So regardless of what the units of my independent, my x variable are, what's going to be true about my test statistic that I find? It's always going to be the exact same. It's a unitless measure. So scaling that x variable or even scaling that y variable shouldn't change that test statistic I see, right? Now, if it doesn't change the test statistic, what else doesn't it change? So what's the area kind of in the tail multiplied by 2 of my test statistic? That would be my, okay. So this is where I'm doing a little bit of review to kind of remind ourselves. If I'm looking at a test statistic, now we said we can use the standard normal to approximate, but Stata can always use the exact student t-distribution we need. If I see a test statistic that's here, or if I see a test statistic down here, maybe this one's a different way than I probably have drawn it before. So let's say this is the test statistic I find, and it's negative, I don't know, negative 1.5. What can I use that test statistic to find? So every critical value is associated with an alpha. Every test statistic is associated with a p-value. How do I find that p-value? It's the area more extreme than the test statistic I found, but that's only the slope coefficients. We always have a two-tailed test, so I would need to take this area and multiply it by 2 to get my p-value. I can then use that p-value, compare it to whatever my desired alpha is. So 90, 95, 99% confidence would correspond to alphas of. So if you don't have this down, this is something we need to have down moving forward. So if I'm looking at confidence levels, I can talk about also significance levels and the corresponding alpha. So if I want to say something with 90, 95, or 99% confidence, the significance levels would be basically that subtracted from 100. So the 90% confidence level is the 10% significance level, or basically I would be failing to reject when I should be, those type 1 errors, 10% of the time. And then here, 95 would be 5%, 99 would be 1%. What if I wanted to say something with 84% confidence? My significance level would be 16, right? And then the significance level is basically alpha. It's just my probability, right, that I've made a type 1 error, but converted into a percentage. So if I have a significance level of 10%, the proportion of times I'll be making a type 1 error would be an alpha of 0.1. 95% or 5% significance, 0.05, 0.01, 0.16 if we chose this weird one, right? But these are kind of our 3 benchmark values we're always going to compare to. Okay? So that's kind of a little bit where we left off, thinking about scaling variables. So I want to do a little bit of review of that. just so we get a little bit more practice in Stata, we're going to come up here. Let's see if I have my global path set correctly today. If not, I can adjust it. I've been moving files around, so I'm guessing I probably don't have the right one. Yeah, I don't. So let's see where I moved that COVID data to. So once again, you're getting practice. Okay, I moved it to the week 5, right? So this is the data set we want, that COVID county data. It should just be on your OneDrive, so you shouldn't have to worry about that file path changing. I moved some things around. So I would highlight everything up to the file, so just what that kind of subfolders would be. I can copy that. My file path now has changed, not from week 4. I moved everything to week 5. All right. So I forgot to update the do file to include that, but it doesn't matter, right? Once I open up that data set, it always tells me that file path. Now, moving forward for the rest of the week, I'll have that kind of that correct file path that I can use where everything's in week 5. So just kind of review of how we find that. So let's think about this example where I wanted to estimate the percent of a county that was vaccinated based off of their income. Okay. So I could do this. In fact, I'm going to add in a regression here. Which takes the original variable of household income, and it uses that to try to predict my y variable. So remember in Stata, when I use this regress command, the first variable is always my y variable. The second variable is always my x. That's nice because that's how we would write it out. Okay. So I run this regression. How would I interpret my slope coefficient? Well, if median household income is just in dollars, it would be if the median household income goes up by $1, the percent of the county that's predicted to be vaccinated would go up by 0.0003%. Well, change of $1, right, is probably going to have a relatively small effect, right? That's what we see here. Right? But that's still how we interpret it. Once again, how do we interpret constants or intercept coefficients? So remember, Stata kind of calls this a constant. Intercept constant is just different names for the same thing. So this is always my predicted y value. It's the predicted percent of a county that's vaccinated if what? The x value is equal to 0. Kind of weird. I can't have a median household income of 0, but that's still how we interpret it. Right. So I have a what type of result here? Is it highly significant or not? Well, what's my p-value? So we have our test statistic and our p-value. When we were comparing test statistics to critical values, remember those are like 1.65, 1.96, and 2.58. My test statistic going to be larger than those? Way larger. I'm rejecting with insanely high levels of confidence, which should correspond to very small p-values, right? My p-value to the third decimal here is 0. I can reject at any level I want to, right? Now, obviously, like at some point, like 99.999%, maybe not, that there's some value somewhere out there, but rounded to the third decimal, this p-value is 0. This is a highly statistically significant result, okay? So what's going to happen? So I'm going to run this code. I'm going to generate the mean and the standard deviation of that income variable. If I subtract the mean and divide by the standard deviation, what should that give me? So that's called standardizing a variable. So this new variable I've created, if it's standardized, it tells me the number of standard deviations away that household income was from the mean. So a standardized value of 0 would mean that household income was exactly equal to the 0 standard deviations away from the mean. It is the mean. If it's 1.5, it means it was 1.5 standard deviations above the mean. It was negative 0.3, 0.3 standard deviations below the mean. Okay? So if I standardize that variable and I then run a regression, still trying to predict the percent of counties, so same y variable, percent of the county that's vaccinated, but using the standardized version. But when I standardize this variable, all I've done is change the units. So when I run this regression, what should be true about my test statistic and my p-value? We said if I change the units, the test statistic and p-value are unitless, so what should change? Nothing. That test statistic and that p-value should be exactly what we were finding before. Now, the slope coefficient itself, what will the interpretation be? Well, now what is a 1 unit change in my x variable? It's no longer representing $1 of income. It would now represent the number of standard deviations away from that mean income. So the interpretation will change when I change the units. Okay. So if I run this regression, I get this new slope coefficient. Now it's still positive, right? But it's going to be scaled to whatever my new units are. So my new unit is if this standardized value goes up by 1. So if the number of standard deviations above the mean that income value is goes up by 1, or it is 1 standard deviation further from the mean, the predicted percent of the county that's vaccinated would go up by 14%. So my interpretation is always in terms of the units of my x and y variable. But we said if I take a coefficient and divide it by the standard error, it's got the same units. My units always cancel out. So notice what happened to my test statistic and p-value. Exactly the same. Right? Doesn't change my rejection decision at all when I scale these variables. Okay. Any questions on that idea? Okay. So we kind of come back here. What if I instead standardize the y variable? Okay. So now I'm going to run a regression where I've standardized the y variable but left the x variable the same. So now the interpretation should be what? So I'm going to run this regression. I'm going to standardize that vaccinated variable, run my new regression here. If I've scaled, before we look at it, I've scaled the y variable now. What should happen to the test statistic and my p-value? If I change the units of a variable, what happens to the test statistic, p-value, or the statistical significance? I said it. For listening to me at all, it just went through an example. What happened to that? Nothing. So a little bit of feedback from you guys means we get through material and can dive deeper into these issues. All right. So if I standardize the y variable, notice I get the same test statistic and p-value. Right. Now my coefficient is going to change because I changed the units now not of the x variable but of the y variable. So now the interpretation is if this household income, my x variable, goes up by $1, the change in my predicted y value, which is no longer the percent of the county that's vaccinated, it's the number of standard deviations above the mean vaccinated percent. So if my income goes up by $1, household income in a county goes up by $1, the number of standard deviations above the mean vaccinated percent in that county goes up by what? 0.00002 standard deviations, right? Because that's the new unit of my y variable. So when we scale these variables, the interpretation of our coefficient changes because it has to adjust to whatever the units of our new variables are, but the statistical significance won't change at all. Okay. In fact, if I look at any of these examples, I can use my p-value and my test statistic to make projection decisions. What else can I use? What's over here on the right-hand side? My confidence intervals. What does the confidence interval tell me? It tells me, and it always defaults to 95%, but that with 95% confidence, the true coefficient, remember, this is just what I found from my sample data, but building my confidence interval around that, with 95% certainty, the true coefficient is somewhere in this range. What are we always assuming that coefficient is equal to? So if 0 is not in that range, what would the rejection decision I make if I did hypothesis testing be? I reject. So in all of these, we were strongly rejecting. So our confidence interval should not include 0. Sure enough, doesn't include it there. Doesn't matter if we have the scaled versions, doesn't include it there, doesn't include it there, right? So scaling the variable, whether we use the test statistic, p-value, or confidence interval, will not change our rejection decision. The only thing that changes is that interpretation of our slope coefficient. Okay. And we could do the same thing. Gets to be kind of weird, the interpretation here. It gets a little bit convoluted. But I just want to use this example to make a further point. If I standardize the x and the y variable, well, what should happen to my test statistic and my p-value? Nothing, right? I'm just scaling these. Sure enough, I find the same values. Now the interpretation gets a little goofy because now it's if the income in a county goes up by 1 standard deviation, then the percent of the county that's vaccinated goes up by 0.33 standard deviations. But maybe this is important, right? Why might I want to talk about changes in terms of standard deviations? Well, if we go back to those original regressions, when I was talking about the effect of a $1 increase, is that very practical? I mean, if I'm looking at the differences across counties, I'm probably seeing thousands of dollars in difference in that median household income. So a lot of times we want to standardize these variables because we know the effect of $1 is going to be so small that if we're presenting this to our audience, how do I even really think about that, right? Whereas a standard deviation increase is really comparable across different variables, right? I can always say that this 1 standard deviation increase causes this change in Y, right? So when we're presenting this to an outside audience, sometimes we might want to use the standardized version, or maybe we just say, okay, it's hard for people to think about the effect of a $1 change. What would the effect of a $1,000 change be? The effect of $1 times 1,000, right? So I could scale up the coefficient by running the regression, or I could just change the underlying variable so that these coefficient values actually look, readable. It's not 0.0000. And that's really just a matter of like presenting to an audience, right? You kind of have to know your audience, know what their statistical background is. But really, I wanted to kind of go through this exercise to prove it doesn't matter if we scale these variables, we always kind of get that same statistical significance. Okay. Any questions on this? We kind of go back to the slides here. Okay. So I'll probably go through this a little bit quickly because we also talked about this last week. But I've been giving you this example right now with continuous variables, right? So what if we have these variables where they're what we call dummy variables or indicator variables, right? So this would be like if I want to know if somebody is over the age of 60, it's a 1 if they are, 0 if they're not, right? I kind of just have this binary variable. So the way I would interpret that slope coefficient is if I belong to the 1 group, right, going from the 0 to the 1 group, that coefficient on that dummy variable is the predicted change in my Y value. So we'll kind of run through some examples here. So the hypothesis testing looks exactly the same. We'll keep using this assumed true value of 0. Nothing changes here, okay? So same kind of steps for doing hypothesis testing, whether we do the critical value or the p-value approach. So let's get some examples here in Stata, right? And we can start to kind of go through some more of these interpretations. Okay? So I have this same data set, and I think I changed, I don't know why. I changed it probably because the numbers are more interesting. I'm sure I did this for a reason. We'll probably see here in a second. I chose some variable that represented the number of new cases of COVID in that county, and then a dummy variable for just was it in the South. Okay. So if I run this regression, what is the interpretation now of a change, a unit change in my X variable? Well, if it's a dummy variable, it means going from the 0 to the 1 group. So being a county that's not in the South to a county that's in the South, we said the predicted number of new cases would go up by 892. So this is telling me that what, I don't know, counties that were in the South, people were probably more likely to be out and about, interacting with more people, and the spread of COVID was high. Now, what levels, a little bit of a trick question here, what levels could I say that's a statistically significant effect at, or what levels could I reject the null that the effect of being in the South was actually 0? Well, if I can reject at 95, we usually want to be a little more complete, right? We have 3 levels. So if I can reject with 95% confidence, I can also reject with 90%. But can I reject with 99? Not quite. We need that p-value to be less than alpha. In fact, this is a rounded value. If it was below 0.01, it wouldn't round it to this. So this is technically like 0.01003, right? It's just slightly above that cutoff, okay? So we need that p-value to be less than our desired alpha. So we can't quite say this with 99% confidence, but 95% is pretty high, right? This is nothing we're going to ignore, right? So just to kind of get some more practice, we could do the same thing, but kind of account for population size. I'm going to skip through this because I don't think it's necessarily that helpful right now. One thing that we talked about last week as well, and now I think I forgot to include it in this week's slides. I sure did. So let's go back because I want to revisit this idea. Nope. Where was I at? So if we go back to last week, where did I have? There we go. Okay. So we talked about this kind of statistic, which was called the R squared, right? So the R squared was basically, there's variation in this variable, this Y variable we're trying to predict, and our X variable is going to be able to explain a certain amount of that variation. If I could explain all of the variation, R squared, the proportion of variation I could explain, what's the highest proportion of variation I could ever explain? A proportion of 1 or 100%. So the R squared is going to be the percent of the variation we can explain with this 1x variable, but in decimal form. So I'll kind of show you where you could grab these values of the explain and the total sum of squares from this data output. But basically, the ratio of those two things will tell us what that R squared value is. So we'll get out of week 4 slides here. Go back to our data output. So I originally had this regression. We're looking at the number of new cases in the South, right? So I think here I changed this variable so we had apples to apples. I'm just going to change the Y variable so that we have the same one in both of these regressions. So I run this regression and I get, it tells me the R squared. So what that R squared is going to be, here it's a little bit different, right, in Stata than what we would usually kind of see in a textbook or talk about it. So it calls it the model's sum of squares. Basically, it's the deviation explained by the model. So our explained variation. Okay? So the amount of variation we're explaining is this number. The total variation would be this number. So I can prove this to myself. If I divide what, 185,000 by 1,040,000, I will approximately get this R squared value right here. Okay? So using that model's kind of SS or sum of squares, it's the amount of variation our model explains. The amount of variation that existed in that Y variable is that total sum of squares. The ratio of the two is the percent of the variation in Y we can explain with our X variable, but in decimal form. So technically it's the proportion of the variation we can explain. If I know a proportion, how do I get a percentage? Simply multiply it by 100, right? So this would mean my model, the proportion of variation that just being in the South explains of the number of COVID cases was about what? 17.8%, 0.9%. It's not, I mean, it's about a fifth of the variation, all right? So this is a pretty important variable, right? If I instead tried to predict the number of new COVID or the number of COVID cases with the percent of the county that's vaccinated, this is going to get kind of weird. I'm not trying to make political statements here. But what percent of the county, right? What percent of that variation in the number of cases was explained by the percent of that county that was vaccinated? About 4%. Which of those variables is going to explain more of the variation in the number of COVID cases? Being in the South, right? So while we were very concerned about people getting vaccinated, we should have been like, well, okay, people in the South are doing something that is explaining more of the variation in the number of COVID cases than even the percent of the county that's vaccinated. Maybe we should focus on what the people in the South are doing, right? Maybe that's what we want to focus our energies on. So that R squared is going to, as long as you have the same Y variable, is going to allow you to identify variables that are more important, essentially, right? Are they explaining more of the variation in that Y variable? Okay? And we could go down the list. We could, run this with other variables and try to kind of find some that matter more or matter less. So instead, what I want to come down to is, okay, sometimes I have these variables in the data set that come in as dummy variables. So it was 1 if it was a state considered in the South, 0 if not. That was a nice dummy variable in the data set. But I can create dummy variables from continuous variables, right? So maybe I want to say, okay, look, I don't think the effect is like maybe linear with the percent of the county that's vaccinated. Or maybe I think it just matters if I can get, above 50% or below 50%. So what I did here was I said, okay, look, I'm going to separate states into what I'm going to call high vaccinated versus low vaccinated states. You're considered a high vaccinated state if your vaccination percentage is above the mean. Now, this is where when we standardized the variable earlier, I already created this mean. If I hadn't standardized, I'd have to create what the mean vaccinated percent was. Okay? So when I create a variable, if I have this conditional statement and I put it in parentheses, what Stata will do is say, create this new variable that if this statement is true, it's going to assign a 1 to that variable. If this statement isn't true, it's going to assign a 0. So what this variable would essentially tell me, and I can kind of look at this to make sure it's doing what I think it's doing in the data, is every time I kind of have, so here's kind of that mean vaccinated variable. Anytime I have, what is it at? A vaccination percent, so 34 here, if it's below the mean, it puts a 0 in that observation. If I instead have a county where the vaccinated percent is 43, which would be above that mean value, it puts a 1, right? So it's creating this dummy variable form. So what I could then do is instead of using that continuous variable, I'm just going to run a regression and say, okay, look, does the median household income, maybe I don't want to kind of have my Y variable be continuous. I just want to know, how does it change the predicted value of Y if my Y is a dummy variable? So we haven't done one yet today, and this is where our interpretations get a little bit different. So my Y variable is now a 1 or a 0. 1 if I'm in a county that has a above the mean vaccination percent, 0 if not. So changes in my Y variable, and we mentioned this last week a little bit, are now changes in what? Well, the only values I can see for Y are 0 and 1. So changes, what are my units in? Close. 0 and 1 would be proportions, right? Or changes in the probability I belong to the one group. So how would I interpret a regression output where my Y or my dependent variable is now a dummy variable? If median household goes up by, income goes up by $1, the change in the probability, it's a high vaccinated county, would go up by point. Remember, we said if we have e to the negative, that means move the decimal 6 places to the left. So it goes up by what? 0.000009, right? Pretty small effect, but probability effects are always going to be small. What's the largest I could ever see the probability change by? Going from 0 to 1. I mean, nothing is ever going to explain, right, the entire movement. So we're generally going to see some pretty low values here when our dependent variable is a dummy variable. Okay, so that's how we kind of make that interpretation when our Y variable is a dummy variable. Okay, and when we can create those variables, maybe this is something like, I don't know, some of the other data sets we've looked at. I want to create a dummy variable. I think this is problem set 1, if they have more than 2 siblings. All right, so I can always create these dummy variables where if this statement in parentheses is true, it assigns a 1. If it's not true, it assigns a 0. Any questions over anything we've looked at? And once again, this is basically a lot of review for the first kind of half or so of this class today. I mean, just we've gone more in depth than we did last week. Any questions over anything here? Maybe one more thing since we have an example here. Is income a decent predictor of whether or not the county had a high vaccination percentage? Well, how much of the variation is explained? What statistic do I look at? My R squared. It's explaining about 8%. I mean, 8% is not nothing, right? With just one variable, if I can explain 8, I mean, that's a decent amount, right? Now, obviously, I'd like this to be closer to 100, an R squared of 1 or 100% as I could get, but this likely means that there's a pretty strong link. So if your R squared is higher, what do you think probably happens to your statistical significance? If it's explaining more of the variation in Y, it's likely that those two things are linked. So is it going to be more or less likely that you can reject the true value is 0 for that slope coefficient? Probably more likely. In fact, at 8% of the amount of variation explained, get a pretty high test statistic, pretty low p-value. So we can reject it very high levels of confidence. The closer that R squared gets to 0, it's more likely we see smaller tests. It's not always a guarantee, but it is more likely we would see smaller test statistics, and then coincidentally, higher p-values, less likely to reject. Okay. All right, so we'll go back to the slides here. This is one thing that we're going to want to talk about before we kind of move on to multiple linear regression. So this is a thing that we have to worry about, and there's an easy solution in Stata. So we're going to go into it. I'll kind of gloss over the technical side of things, but I'll give you kind of the intuition. So our error terms, those standard errors, what we always assume is what we call that they're homoscedastic. And I'll kind of give you some visuals that explain this in a second. Now, they can be what we call heteroscedastic. Okay? If they are, typically our homoscedastic errors are going to be a little bit smaller. Okay? So let's think through this before we kind of go through the steps. How do I calculate my test statistic? It's simply that slope coefficient divided by my standard error. If I treat the errors as homoscedastic, I said they're typically smaller than what they should be. So if my standard errors are a little bit smaller than what they should be, what's going to happen to the size of my test statistic? It's going to go, well, if my denominator is smaller, this fraction would be higher. If my test statistic is higher in absolute value, what's going to happen to the area to the right of it times 2, which is my p-value? If the test statistic is higher, my p-value is going to go. What's happening to the area to the right? It's getting smaller. So my p-value is going to be lower. If I only reject when that p-value is less than alpha, if my p-value is going down, is it more or less likely I reject? More likely. So if I incorrectly treat these standard errors as homoscedastic, it's going to be more likely I reject the null, even though I shouldn't be. So I might find a statistically significant effect, even though there isn't one. So what can we do, right? So we know that our standard errors might be wrong. And then we kind of went through the steps of why that's a problem, because it's going to make it more likely we reject, even though we shouldn't be, right? And I'll show you kind of this in Stata here in a second. Oh, where's my homoscedastic slides? Did I skip through them on accident? Yes, I skipped ahead on accident here, right? So I explained kind of that intuition of homo or heteroscedastic errors. I'm going to go back here to kind of give you some nice visuals, okay? So what homoscedastic errors means, so that I went back, sorry, I have the audio and not the visual. That would help. There we go, right? So we just kind of talked about kind of through this slide, what if, what is the actual technical definition of homoscedastic errors? So it means that the variation that exists in the error term, or how much my predictions are off by, does not depend on the value of X, okay? So a visual of this, if I had homoscedastic errors, so I think the example I had here, I grabbed this from a textbook, I kind of cheated. So I've got student-teacher ratio, and then I have my Y variable I was trying to predict was test scores. So if I have higher student-to-teacher ratios, that means that each teacher has to deal with like more students, right? Which means they're less likely to give individualized attention. So when that student-teacher ratio goes up, test performance of the student actually goes down. This is why ideally I like teaching classes like this as opposed to my B251 where I have 300 students, right? I know that's going to impact their test scores. Okay? Now this is high school data, but the same logic would apply. Now homoscedastic errors mean regardless of the X values, so regardless of the student-teacher ratio, when I'm looking at how much my predictions are off by, so this is like my line of best fit. If I had the scatter plot, this was my line of best fit. This was that linear regression with the intercept and slope coefficient I estimated. For any X value, the variation in how much I'm off by, if it's the same regardless of that X value, that's what we would say is homoscedastic errors. If for higher values of the student-teacher ratio, there's more variation in the data and my predictions are off like by more extreme values, notice what's happening as the X value goes up, the distribution of those errors I'm making is getting wider, or the variation in my predictions is getting larger. Right? Maybe a better way of looking at this, if I had to draw a line that best fit this data, I would probably draw it like something, maybe it's kind of flat, but a little bit downward sloping. But notice, when I come up with a prediction, it's for one specific X value. So when I think about my line of best fit, there is only a single prediction here. And in every observation, my prediction is wrong, right? Now we're trying to make the prediction that makes the smallest amount of errors, or if we go all the way back, we're minimizing the sum of those errors that we're making squared, right? Over penalizing extremely bad errors. If I'm making a prediction for this value of like 4, notice if I had one value here, my errors are how much that would vary from the actual data. There's a very wide distribution of errors that I'm making down here. But if I look at higher X values, what's happening? If I had one point here, how much variation or how bad are my errors here? It's a lot tighter of a distribution. The variation in the errors I'm making is different for high versus low X values. The error depends on the value of X. If it depends on the value of X, we would say that is actually heteroscedastic. There's a difference, right? Homo meaning kind of the same, hetero meaning different, right? So this is like a nice example of heteroscedastic errors. So if I incorrectly run this regression and treat them as homoscedastic, I end up with that problem that my standard errors are too small. I'm more likely to reject the null. Okay. Maybe another example just to get at the flip side. If I had to draw a line that kind of best fit this data, I mean, I would argue, maybe it looks like it's a little bit positive here, but if I draw it across the whole data set, it's pretty flat. If I look at my predictions here, no matter what X value I'm looking at, my errors kind of have the same distribution, right? So here, the value of X, the variation of my errors, it's always the same. It's homoscedastic. My errors are the same regardless of that X value. Is that kind of making sense a little bit? I know this is a hard kind of concept to think about. And we're here just kind of eyeballing it. So there's ways we can actually measure it here in a second, which we'll dive into. But I think seeing the visual, hopefully, here we can see if I drew a line that best fit this data, the errors are about the same no matter what value of X I'm looking at. Whereas here, there's a lot more variation in the data down here than there's going to be at these higher X values. Okay. Any questions on this idea before we jump into state and see maybe how we do some actual statistical tests for whether or not the errors are homo or heteroscedastic? Yeah, so maybe I'll draw something that kind of combines both of these for us to kind of help. So I think personally, the easiest way to think about, I don't know why. Maybe it's because we assume that errors are homoscedastic, but I always think about like heteroscedastic. It's easier for me to draw that out for some reason. So if I think about any X and Y variable, if I were to draw heteroscedastic errors, so before I do that, just as kind of a reminder, I probably mentioned some of these terms and you're like, oh, I kind of forgot what we were talking about. What is the error term? Well, if I have a scatter plot of data, what we're doing with simple linear regression is trying to come up with a line that predicted Y for any possible value of X we were interested in. Now, for any one observation, for this X value, we will always come up with the same predicted Y value. But for any one observation, the actual Y value is going to be a little bit different. That difference between the actual and the predicted Y, this is what we were calling our error term or epsilon, right? That's just the Greek letter. I'll typically say error because I honestly forget what Greek letters are called sometimes, right? I know the basic ones, but sometimes I trip myself up looking at an uppercase or a lowercase Greek letter, but it is epsilon, but I'll call it the error term. That's what it actually represents, okay? So if I had heteroscedastic errors, what that's telling me is that if I had a line of best fit, so I'm just going to assume I've got a positive slope coefficient. And when I estimate this equation, I have a positive slope coefficient. That means that when I'm looking at X values down here, some of my errors are really large this direction. Some of my errors are really large in this direction. So if I think about the distribution of my errors, that's where we were kind of thinking about it's relatively wide, right? Now, when I'm looking at really high X values, maybe my data is more grouped here. So let's say down here, the scatter plot looked like that. Up here, these are the observations I see. Well, what's happening to the errors I'm making at higher X values? They're not as large. The distribution is much tighter. Or basically, the variation in that error term when X is, really high is not the same as the variation in my error term when X is really low. Or the variation is not the same, it's heteroscedastic. Okay? And then you could do a similar thing where it's kind of grouped always the same, and that would be homoscedastic. Okay? Now, in practice, there's also data in the middle, right? But I'm just kind of using these two extreme points. So maybe the rest of the data looks like this. So maybe the variation is a little bit different here than it was here, and it's different than it was here, right? So at any X value, if I have any variation in my error term, that would be heteroscedastic. Any questions on this idea? Like I said, for me, the images help solidify this idea. But I'm not going to ask you to draw an image, right? I'm going to be more focused on what is this incorrect assumption? So we always start out when we run these simple linear regressions. We're doing so assuming the errors are homoscedastic. If they are heteroscedastic, we said the standard errors are going to be wrong. Now, I said typically they're smaller, which made it more likely we could reject. But it doesn't have to be the case. So we'll actually look at some examples where it can go in either direction, right? So what is our solution? Okay. So if we go back to that regression file, kind of left off here, I'm going to kind of go into this exploring homo versus heteroscedasticity. Okay. So here I'm going to look at this just to give us some more visuals. This is one where if I look at cases per person and the percent of the county that's vaccinated, this is where it looked pretty homoscedastic. Doesn't matter what X value I'm looking at, the distribution of the errors I'd be making from the line of best fit are always about the same. Now, an example where that's not the case would be if I instead look at household income and the unemployment rate. That's the one where there's a lot more variation down here. I think the reasoning here is high unemployment rate counties sometimes are a result of having low income in those areas, but also sometimes a result of the political leanings of those areas, and higher income tends to be, think about Bloomington, it's pretty liberal, right? And so we have more variation because there's different things explaining the variation in unemployment, or there's explain the variation in income depending on the unemployment rate. I'm not going to dive into intuition. That's kind of a different economics class, but that would be kind of maybe a reason why we see this. So instead, I don't want to look at the graphs now. I'm just going to run the actual regression for the number of COVID cases per 1,000 people and the percent of the county that's vaccinated. So just to get some more practice, how do I interpret my slope coefficient? So the units, we said my Y variable is now the number of cases per 1,000 people, and vaccinated is still the percent of the county that's vaccinated. So if my X variable goes up by 1 unit, or the percent of the county vaccinated goes up by 1%, the number of cases per 1,000 people goes down by 0.25. Okay. Is that a statistically significant result? Or what levels could I reject the null at? What's my p-value? So I can reject at all of my conventional levels. Okay, pretty strong result. In fact, even though the R squared is relatively low, very highly statistically significant result. So I'm worried that statistical significance is driven by the fact that I treated the errors as homoscedastic when they were in fact heteroscedastic. So I can run a test for this to make sure that the errors are in fact heteroscedastic. So when we were looking at that scatter plot, that was the example where maybe there was some heteroscedasticity. Right? So after you run a regression, if you run this command stat imtest, It's a built-in kind of test. We are not going to dive into the technical side or the theoretical side of what it's doing, but it's basically testing for, is there variation in the errors, and is that different at different X values? So it can do all this work behind the scenes, and we don't have to worry about what it is. All we have to worry about is that it gives me a test statistic, just like we have the slope coefficient, and we can convert that into a test statistic. It develops a statistic that measures heteroscedasticity and converts that into a test statistic. And then everything goes back to exactly the same as we were doing before. So here, it reports to me the p-value for that statistic on heteroscedasticity. So we always start out assuming, what did I say earlier? Every regression we've looked at this point assumes the errors are homoscedastic. So this says, can I reject that assumption, right? Well, with a p-value of 0.07, what levels can I reject that? Maybe that's the easy place to start out. Yeah, is that p-value less than 0.1? Yes, so I can reject at the 90% level. Is it less than 0.05? So I fail to reject with 95% confidence. Because I can't reject with 95, I definitely can't reject with 99. It's not going to be less than 0.01. So I can make the reject, but what am I rejecting? Once again, this test is for the null hypothesis that the errors are homoscedastic. So instead of kind of worrying about the technical null hypothesis and the fact that what this actually means, so I'll draw kind of exactly what we're thinking about. The null is technically that variation in my error terms for different values of x is always the same value, some constant, right? For us, all we are going to be thinking about is simply my null is that the errors are homoscedastic. That's all that means, right? So when I ask you if you can make these rejection decisions, what we're rejecting is the null hypothesis. We start out assuming the errors are homoscedastic. We found a p-value of 0.07, which was less than 0.1. So with 90% confidence, we can reject the errors are homoscedastic. Or we found significant evidence that the errors are in fact heteroscedastic. Okay? So if we can reject the null when we're doing this test for homoscedasticity, what we are rejecting is homoscedasticity. Let's see if I can spell this right, I'm writing quickly. Or essentially what we found evidence of is that the errors were in fact heteroscedastic. Okay. Any questions on this before we go back to stating? I get worried when I don't get questions. Okay. So what do I do? Right? My regressions always assume homoscedasticity, and I have evidence that they're not homoscedastic. Right? I can reject with 90% confidence that they are homoscedastic. Well, luckily, Stata is much better than us, and we can actually adjust these errors. Right? So if I run that same regression, it assumes homoscedastic errors. We ran this test and we said, okay, they're not. All you have to do is one of these two options. So I run that same regression, but I put on this added command that I want to run the regression with what we call robust standard errors. Basically, I want to adjust those standard errors for the heteroscedasticity. That will then give me my new standard errors, which account for the fact that there was heteroscedasticity in my errors. So what we'll notice, if I run the original regression, and then I'm going to run the kind of new one that accounts for the heteroscedasticity, notice I get the exact same slope coefficient, right? That's not going to change at all. But the whole reason I was doing this is because I didn't think there was a problem with the coefficient. I thought there was a problem with my standard errors. Okay? Remember, that's kind of the setup I did. The standard errors are too low. So when I treated it as homoscedastic, if my standard errors were too low, 0.021 instead of 0.022, that made my test statistic a little bit higher. And even though I can't see it, this could be like a quiz or an exam question. Which of these p-values do I know has to be smaller? If I have a larger test statistic in absolute value, what's going to happen to the area to the left or right of it? Smaller, right? The larger the test statistic, the further out I'm getting into the tail, the area in the tail is getting smaller and smaller, or my p-value is getting smaller. So even though I can't see it to the third decimal, I know that this regression with a higher test statistic actually has the smaller p-value. So it was more likely I rejected the null when I didn't adjust for that heteroscedasticity than when I did. Okay. Any questions on that before we keep moving? Okay. So once again, I would go back to kind of what helps thinking about is kind of drawing these like arrows as directional changes. If my standard error is too low when I treat it as homoscedastic, then when I adjust for that, my standard errors will then be higher, which will lower my test statistic, which increases the p-value, which makes it less likely I reject, which is what we just saw in those results. When I adjusted for the heteroscedasticity, it lowered my standard errors. Right? Sorry, I said it lowered. When I adjusted for it, it increased my standard errors. My standard errors were too low before. So my standard errors are now higher once I adjust for that heteroscedasticity, making my test statistic smaller. Even though we can't see it, we know the p-value is larger because of that test statistic is lower. And then if my p-value is lower, sorry, if my p-value is higher, we know that we're going to be less likely to reject them. All right. Any questions on this idea? So this is one thing I just want to kind of reiterate. Adjusting for that heteroscedasticity did what to my coefficient estimates in terms of the actual size? My coefficient on the slope and the intercept are exactly the same. What did it do? It changed my standard errors, which gave me different test statistics, different p-values, and different rejection decisions, potentially. You know, in both of these examples, I don't know, did it really matter that I treated them as homoscedastic? No, the p-value is very slow, very, very low. But you can imagine a different data set where it could change that decision. Maybe the p-value goes from 0.07 to instead being 0.11, which would then change my rejection decision. So I've got another example, which is kind of weird, right? So I'm going to come down here. And now I have a metro variable. So this was the county considered to be in a metro area? So this is like counties around Indianapolis, Chicago, right? These are like kind of urban kind of areas. Whereas a 0 would mean it's not considered to be in a metro. So I could think about it almost like the 0 group is like rural areas. The 1 group is larger cities. Okay. I want to try to predict whether or not I'm looking at a county that's in a large metro area based off the unemployment. So my dependent variable is a dummy variable, but unemployment is nice and continuous. So how would I interpret my regression results here? What's a 1 unit change in my X variable? The unemployment rate goes up by, I think here I have it in terms of percentages. So if it goes up by 1%, the predicted change in my Y variable, which if it's a dummy variable, what is the units? Changes in the probability that it belongs to the 1 group. So if the unemployment rate goes up by 1%, the predicted probability that it is a metro county goes down by 0.045. If that's the change in the probability, I could also say that it goes down by what? 4.5%. Pretty low R squared, right? It's not explaining a large amount of the variation in whether or not a county is a metro county, right? Is it statistically significant? Yes, right? P-value is 0, so any level I can reject. Now, here's a weird case where maybe I think, so let's say here, I think it's S-stat, right? Is that what I want? I had it up here. I forgot where, there we go. Sorry. So this kind of pre-packaged like set of things, S-stat, IM test, that's kind of how we ran this test for heteroscedasticity. So here, can I reject that the errors are homoscedastic? My p-value is 0. So I can reject that very high levels. I should not be treating this as that has homoscedasticity. So I need to adjust for this. It's an easy fix. All I have to do, and I think before I showed you adding this VCE robust, outside of this course, this is probably the more appropriate way to do it. But ultimately, it gives you the same thing if you simply just type in the word robust, right? There's a reason why that would be like the next level of econometrics that we would talk about, because the actual package behind the scenes is doing something slightly different. But for the sake of what we're doing, VCE robust or robust does the same adjustment for those heteroscedastic errors. So when I now run this regression, notice what's going to happen to the size of my coefficients? Nothing at all. The only thing adjusting for that heteroscedasticity does is it changes my standard error. So I said typically, if we treat this as homoscedastic, usually our standard errors are too small. That was the first example we looked at. Here's a weird example. 0.0046. Now it's what? 0.0042. This is a weird case where it's not always that our homoscedastic errors are small. This is an example where, in fact, they were larger. Right? So it can go in either direction. It really just depends on what that scatter plot of data would look like and where the heteroscedasticity exists. For us, right, I would either give you results to where you can see what happened to that standard error, right? And then maybe I leave out the test statistic here. So let's say I just gave you the coefficient and the standard error after you adjusted. If the standard error goes down, once I adjusted for this heteroscedasticity, if the standard error is now smaller, what happens to my test statistic? My test statistic was the coefficient divided by the standard error. So if that denominator is smaller, my test statistic will be larger. If the test statistic is moving further into the tail, the area in my tail is going down. My p-value is smaller. Am I more or less likely to reject? More likely. So it's the same line of thinking we can chase down to what's going to happen to our rejection decision. We just need to actually run this regression where we've accounted for the heteroscedasticity to see how does it update or how does it adjust our standard errors. Now, typically, it'll look like the first example, but I kind of actually had to take a while to find an example where this is the case because it often isn't, but it can go in the opposite direction. Okay? You mean just to, all you have to do is run your regression and put comma robust. That adjusts for the fact that you have heteroscedasticity in your error term. So really in practice, there are things that will be homoscedastic. When you get to higher levels, if you look at what researchers are doing, they just always assume like if you have large enough data sets, you can almost always say the errors are heteroscedastic. So they almost always throw this in at the end, right? In fact, it's kind of just like a fail safe. Like even, it's a way to adjust, even if there is a small amount of heteroscedasticity, most of the time you would just see this added into the regression. But it's a really simple fix, right? All we have to do is kind of add that command in, and all the work behind the scenes, which is like much more complicated mathematics, Stata can do all that behind the scenes for us. So we don't even have to worry about it, right? This is applied econometrics, not theoretical, right? So we're kind of just more focused on what packages do we have in Stata or R can do a similar thing that will adjust for this heteroscedasticity. Any other questions on this before we keep moving? Okay. If we had more time, I would go through this. It's not really crucial. So we have some time on Thursday's class. Maybe I'll review this a little bit. It's a different way of looking at heterohomoscedasticity, but we spent a good amount of time on it today. And I think we got a lot of good visuals. There's another way to think about it. But really my focus was using that IM test command to identify if we can reject or fail to reject that the errors are homoscedastic. And then once we adjust for them using that robust command, can we determine what has happened to our likelihood of rejecting based off of the change in our standard errors, the change in our test statistic, p-value, et cetera. Okay. So that leads us to multiple linear regression, which I think we'll kind of touch on this at the end of class. We'll revisit this, basically start with that on Thursday. But I wanted to talk a little bit more about this R squared and the adjusted R squared. So I want to introduce this concept now I will gloss over one part of it that we will then revisit probably later on in Thursday's class. So anytime I was looking at this data output, it was giving me an R squared, but it was also giving me an adjusted R squared. So what the adjusted R squared is going to do is, for right now, we're just going to focus on the fact. So what we said our R squared was the explained sum of squares over our total sum of squares. So we said this was kind of like the proportion of variation our x variable explained. Okay. Well, that would be the same as 1 minus the proportion we can't explain, right? If I can explain 100% of the variation, or sorry, 90% of the variation, the percent I can't explain would be 10%, right? So I can always kind of go back and forth. So here, what we're going to call the amount of variation we can't explain is the residual sum of squares, or basically those errors that we were making. What proportion of the variation in y were those errors, right? So R squared was the proportion we can't explain. That's the same as 1 minus the proportion we can't explain. Now, what the adjusted R squared, and here, technically, I always write in the word adjusted here because I think it makes it easier. If you're looking like in a textbook, they throw a bar over it, and that's your adjusted R squared. Just trying, and I'm not trying to trick you or try, right? So the adjusted R squared, I'm just writing as adjusted. But if you look at like the textbook or some of the notes, I'll write it as R squared bar because that's technically the notation we should be using, trying to make things a little bit easier, just so we're talking about the adjusted R squared here. So the way that we'll do this is, I now have this different way of writing my R squared, all right? But the adjusted R squared is going to take that proportion that we can't explain, and it's going to adjust it by this fraction, okay? Now, what this fraction is going to do is say, if I have a small data set, what do you think happens to the amount of variation that I can't explain? It's likely going to be higher. I don't have as much data. The more data I can get, the proportion that I can explain is going to go up, or the proportion I can't explain should get smaller and smaller. So what this will do, notice, if I have n, use red here, if n is going up, so I'll use some hypothetical examples to make this point. Let's say I start out with an n of 3. What is the value of this fraction? And let's assume just for now, with a simple linear regression, k is going to be the number of variables we include on the right-hand side. Up to this point, we've only ever included one x variable. Next class, we'll start to talk about if we can add in not just one, we can do 2, 3, 4 variables on the right-hand side. So if n was 3, what would this fraction be? 3 minus 1 is 2. 3 minus 2 is 1. So this scaling factor would be 2. Okay. If n instead was like 100, what does this become? 99 over 98. As n goes up, what is this fraction getting closer to? So if I have 99 over 88, this is really close to 1. Right? So as n goes up, this fraction is going down. It's getting closer and closer to 1. If this fraction is going down and I'm subtracting that from 1, what happens to my adjusted R squared as a result of that? So if I'm subtracting a smaller number, my adjusted R squared should be larger. If I take 1 and I subtract 0.5, if I then take 1 and subtract 0.3, what happens? My adjusted R squared goes up. So I can always put hypothetical numbers to this to kind of remind myself, but it's really all you can use directional changes as well. So as I increase my sample size, that lowers this scaling factor, which then I'm subtracting a smaller amount, it's going to increase my adjusted R squared. So basically, one of the purposes of the adjusted R squared is that it adjusts for what my sample size was. I know that when I have larger sample data sets, right, I'm now adjusting for that same proportion that I can't explain, right? So this could be the same value if I had 10 observations or 1,000. I would end up with the same R squared. What the adjusted R squared does is say, okay, even though you have the same proportion that you can't explain, if you found that, but from a really large data set, we're not going to be as concerned with it, right? If I found it from a very small data set, I should be more concerned that I couldn't explain a large amount. So when we had small sample sizes, this would be relatively large, and it's going to reduce my adjusted R squared. Okay? So the thing that we can think about right now is how that sample size impacted our adjusted R squared. What we'll talk about next class is we don't just have to use one X variable, we can use multiple X variables. We'll talk through how that changes our interpretation, how it changes our rejection decisions, how it impacts our adjusted R squared. And a lot of this, there's going to be a lot of things that don't change, and there's going to be really minor things that do. All right, so a lot of this, like why I'm spending a lot of time on this very simple linear regression, is because multiple linear regression reuses a lot of the same concepts. We just get to add like a couple additional statements, and we can start to think about slightly more complicated topics, but it's going to be reusing everything we've talked about with simple linear regression. Okay, so excuse me. On Thursday's class, we will basically pick up kind of where we left off in our slides. So we've kind of now talked about the adjusted R squared, at least as far as I want to for now, just kind of thinking about how N impacts it. We'll talk more about what happens when K changes after we talk about multiple linear regression. So I left this slide open for what we kind of just worked through. We'll then start looking at multiple linear regression, talking about emitted variable bias. So we'll just kind of pick up where we left off. The data set that we will use. So we've looked at this regression in class part 2. I tried to kind of separate these up into what we did last week versus what we did this week for simple linear regression. We're going to then start using the multiple linear regression file, which is up on Canvas. So we'll start using this one on Thursday's class. I had a question that I had as practice. So we may have an in-class quiz on Thursday's class. May have a quiz in Thursday's class. One question that I kind of took off, a couple questions I took off, which are kind of related to what we talked about today. I might post this just to give you some like additional questions to kind of think through based on today's discussion. The in-class quiz I use on Thursday will be just related to what we talked about on Thursday. So I'll post this. It is not for points. That's why I named it practice, but it would be questions that kind of line up to what we talked about today in class. Okay. I also, since we have 2 minutes and I have you right here, I'm worried about people falling behind based off the attendance in this class. So I'm kind of talking to the wrong group for that. So what I want to talk to you about is I have a B251 exam Thursday. My office hours tomorrow have changed, or they're going to be the same. I'm going to move them back. I imagine they'll be very busy, right? So I'm going to add some office hours on Friday morning. I should be here on Friday morning. If you want to stop by tomorrow during regular office hours, if you're working on that problem set or thinking about studying for that quiz, you can. I'm just giving you fair warning. The line might be long. I don't want you to have to wait. Like, I don't know if you're in a hurry, like I might not get to you because I mean, you literally could be waiting 45 minutes depending on where you show up in place of line. So I'm going to add some additional office hours on Friday. So look for an announcement about that. I won't be adding those to my B251 courses. So it's just for you guys. And then if you do want to meet, I should be around most of the day Friday. So even if those office hours don't work and you kind of have like 1 or 2 last minute questions that you just want to get some answers on before you turn in that second problem set, feel free to email me. We can kind of try to schedule a short time outside of those office hours on Friday. But I did want to make you aware of that just because the day before the exam, it's a lot. Okay. Otherwise, I will see you guys on Thursday. Enjoy the nice weather. It's going to change the weather, and I'll see you then.